this lesson for 1.3, which is just functions. We're going to do a couple things within this lesson. First, look at what a function is, tell whether or not certain situations are functions, work with function notation, and plug in different values for your variable to evaluate functions. We're also going to talk about domain and range. So if we look at the first page here, a lot of words, but it practically tells you that within a function, you have something that you have a relation that is assigned to an outcome. Okay, so you have an input and you have an output with these functions. Your inputs are your domain values. They are your x values. Your range or your y values are your outputs. So make a little bit of a little note on there, just so that way you know that domain is x, range is y. It tells you in that highlighted section that your domain is your inputs, your range are your outputs. So that's something else that you might want to highlight. Within there, it tells you that you have a function if you have exactly one output for each input. So your input values, your x values, cannot repeat themselves. Okay? If we look at, again, this page just tells you input, output. Your input is your x values, your output are your y values. It gives you different characteristics for your functions. It tells you that each element of A must be matched with an element of B. A is your input, B is your output. A is your x, B is your y. So for each x must be matched with an element or a y. It tells you that some elements of B may not be matched with any element of A. So some y's may not be matched with any x's. Two or more elements of A may be matched with the same element of B. So your y values can repeat, but your x values cannot. So x values cannot repeat. If you want, again, x values cannot repeat. And then it tells you for the last one, an element of A, your domain, your x value, cannot be matched with two different elements of B. Again, your x values cannot repeat. To determine whether or not relation is a function, you have to decide whether each input value is matched with exactly one output value. When any input value is matched with two or more output values, the relation is not a function. So if you, like, for example, have x values and y values, let's say your x values are -4, 6, 3, and 9. And your y values are 2, 3, and 7. If you are told that your -4 has y values that go with it that are 2 and 3, this is not a function because you have more than one x value for each of those y values. Your x value repeats itself. That means you have ordered pairs of -4, 2, as well as -4, 3. You can have one that is 3 to 3, so that's 3, 3. So your y values can repeat, but because your x values repeat, it is not a function. If we look at some examples that are there for us on this page, we're told to determine whether each relation represents y as a function of x, which means your x values cannot repeat. If we look at example A, you have input values or x values of 2, 2, 3, 4, and 5. Your output values or your y values are 11, 10, 8, 5, and 1. Because these 2's repeat themselves in your x, this one is not a function. For B, you have points plotted on a coordinate plane, or ordered pairs plotted on a coordinate plane. With these, in order to test a function that's given to you on a coordinate plane, you can use your vertical line test. Your vertical line is a line that's straight up and down. So if you draw a vertical line through any of those points or any of the part that's drawn on your coordinate plane, there should only be one point that crosses that vertical line. So let's say we draw a vertical line through this point here. There's no other point other than this one that crosses that vertical line. Same with if we drew one through this point. Again, there's no other point other than the one point that crosses that vertical line. Through your y-axis, you have 1 point. Through your x-axis, you have 1 point. And then lastly, you have a one point there. So because of this one with your vertical line that goes through each of those points, that those points only cross once throughout that vertical line, or touch that vertical line once, then this one is a function. If we look at the next part, it tells you about independent and dependent variables. Your independent variable is always going to be the x. X is the independent variable. Your y is always the dependent. One depends on the other. You can't get y unless you have x. Okay, so your domain of the function is your x value. Your range is the y value. So you can't get a range or have a range unless you have a domain or an x value. Next, we're going to look at function notation. These inputs and these outputs, your input is your x, your output is your y. Sometimes or not sometimes, but within function notation, your function is named something. In most cases, it will be named f, or you'll see f of x instead of y is equal to. F of x, g of x, h of x, q of x, they're all going to be equivalent to y. So they all mean the same thing, and they are all your output or your dependent or your range. Okay? Within these functions, in function notation, you are going to be plugging in values for the x to find for y. So you'll be given an input, told to plug that in, and get your output. When you designate what your output is, it's always going to be the name of that function is equal to something. So if we look at your next example, it tells you let g of x equal negative x squared plus 4x plus 1. Find each value of the function. It gives you a is g of 2, b is g of t, and c is g of x plus 2. So with all of these, the part that's in the parentheses after the g is what we're plugging in for x in that negative x squared plus 4x plus 1. So if we look at example A, we have g of 2. So that means that we're going to do g of 2 is equal to the opposite. There's an x, so we're going to put the 2 in for x squared plus 4 times x, which is 2, plus 1. From here, we're just going to simplify. Use your rules for order of operations. So do whatever is in parentheses first, then your exponents, multiplication or division from left to right, addition or subtraction from left to right. So next, if we simplify this, we're going to simplify that power of 2. So that's the opposite of 2 squared, which is the opposite of 4, plus 4 times 2 plus 1. From here, we'll simplify the negative times the 4, and then the 4 times the 2. So that's going to give us g of 2 is equal to the opposite 4 is negative 4, plus 4 times 2 is positive 8, plus 1. Your negative 4 plus 8 gives us 4. If we add 1 to that, that gives us that g of 2 is equal to 5. So in our answer, we actually put g of 2 is equal to whatever it simplifies to, which in this case is 5. For example, B, we have g of t. So now we're going to take wherever that x is and replace it with t and simplify. So g of t is going to equal the opposite of t squared plus 4 times t plus 1. If we just get rid of these parentheses, we're going to have g of t is equal to negative t squared plus 4t plus 1. For example, C, we have g of x plus 2. So for this one, we're going to plug in the x plus 2 anywhere we see the x in that negative x squared plus 4x plus 1. So we're going to have g of x plus 2 is equal to the opposite of x plus 2 squared plus 4 times x plus 2 plus 1. The first thing we're going to do is that x plus 2 squared. That is telling you, to do the opposite of x plus 2 times x plus 2. So you're going to have to FOIL that out. So that's going to give us the opposite of x squared plus 2x plus 2x plus 4 times x plus 2 plus 1. From here, combine your like terms within that polynomial or that 4-termed polynomial in the parentheses, and that's going to give you g of x plus 2 is equal to the opposite of x squared plus 4x plus 4 times x plus 2 plus 1. Next, we're going to distribute that negative into the x squared plus 4x plus 4. We're also going to distribute the 4 into the x squared plus 2. So this is going to give us g of x plus 2 is equal to negative x squared minus 4x minus 4 plus 4 times x is 4x, 4 times 2 is 8, plus 1. From here, we're just going to combine like terms. So we're going to have g of x plus 2 is equal to the negative x drops down, the negative x squared drops down. The negative 4x and the positive 4x are opposites, so they cancel each other out. Then you have negative 4, positive 8, and positive 1. 8 minus 4 is 4. 4 plus 1 is 5. So that's just negative or the opposite of x squared plus 5 for your answer. All right, so for our next set of examples, we are going to let f of x equal 3x minus 9, and we're finding each value of the function. So for a, we have f of negative 2. So wherever we see that x, we're going to just plug the negative 2 in and then simplify. So f of negative 2 is going to equal 3 times negative 2 minus 9. Do your multiplication first. So that's f of negative 2 is equal to negative 6 minus 9. Double negative, or negatives, keep the negative, then add the numbers. So that's f of negative 2 is equal to negative 15. For b, we have f of x squared, f of x squared plus 4. So that means that we're going to take the x squared plus 4 and plug it in for x in the 3x minus 9. So it's going to give us 3 times x squared plus 4 minus 9. First, we're going to distribute that 3 into the parentheses. So 3 times x squared is going to give us 3x squared. Then 3 times 4 is 12. And then we have that minus 9. So from here, just combine your like terms. And that gives you f of x squared plus 4 is equal to 3x squared plus 3. All right, so if we look at example C, we are 3x minus 9. So for C, we have f of 1/6. So that's going to mean that we are f of 1/6 is equal to 3 times 1/6 minus 9. Yeah, okay. So with this one, we're going to multiply the 3 times the 1/6. That gives us f of 1/6 is equal to 3 over 6 minus 9. That 3 over 6 can simplify to be 1/2. So we'll simplify it to 1/2 and then subtract the 9 from it. That 9 is the same thing as 9 over 1. In order for you to add or subtract fractions, you need like denominators. So your first fraction has a denominator of 2. That 9 over 1 has to become something over 2. So we'll multiply top and bottom of that fraction by 2 to give us f of 1/6 is equal to 1/2 minus 18 over 2. The 1 minus 18 is negative 17. So that means that f of 1/6 is equal to negative 17 over 2. And then you can leave it as an improper fraction like this. For example D, you have f of 5x squared plus 3x minus 1. So we're going to take that entire thing and plug it in for x in the 3x minus 9. So that means we're going to have 5 of x squared plus 3x minus 1 is equal to 3 times 5x squared plus 3x minus 1 minus 9. So we're going to distribute that 3 into that trinomial. The 3 times 5x squared is 15x squared. 3 times 3x is 9x. And 3 times negative 1 is negative 3. From here, we combine like terms with whatever we have. We still have that minus 9 after that minus 3. So that gives us like terms with that negative 3 and that negative 9. So our answer for this one is just f of 5x squared plus 3x minus 1 is equal to 15x squared plus 9x minus 12. Yesterday, when we went over the first half of 1.3, we worked on telling whether or not something is a function. So if your x value is repeated, it was not a function. We also said that within an equation, if y is raised to a power, it's in the denominator of your fraction, or if it is in absolute value bars, it is not a function. That's if you're given an equation. We also substituted in specific things or evaluated functions. So if we were given something like f of x is equal to 3x minus 9, which was the example from yesterday, and we were told that we're finding f of negative 2, we would just plug in that negative 2 for x and then simplify. Today we're going to start by looking at the domain of a fraction. When you're looking for the domain of the fraction, your domain values are your x values. They're your input values. They're your independent. So you're looking for whatever x can be. If you look at this function, this f of x is equal to 1 over x squared minus 4, you have to look to see where x is to find out what your domain is. Your domain values are what is possibly plugged in for x. If x is just x squared, anything where it's not in the denominator, it's all real numbers. X can be anything. However, with this one, your x is in the denominator of your fraction. So whatever expression that x is a part of in the denominator of that fraction, you're going to set not equal to 0 and solve for what x can't be. anything else is what x would be able to be equal to, that you could plug in for. So if we take that x squared minus 4 and we set it not equal to 0, we would just move the 4 over, adding it to both sides. That would give us x squared is not equal to 4. And then we take the square root of both sides. Remember, if we take the square root of both sides, we have that plus or minus in front of our answer. So x cannot equal positive or negative 2. So your domain would be all of the values except negative 2 and positive 2. I'm pretty sure we went over this in the beginning of chapter 1. So I think it was like in 1.1 or something like that. For an example like this, where you have something like f of x, let's write this correctly, f of x is equal to the square root of x. Again, you want to find what x can equal. You can't take the square root of a negative number, so whatever the expression is that x is involved in underneath the radical, you would set to be greater than or equal to 0. So that x would be greater than or equal to 0. In this case, there's nothing in front of the x or on the same side of x, so your domain would just be the values that are greater than or equal to 0. If we look at example A, it tells you to find the domain of the function given the ordered pairs of negative 3, 0, negative 1, 4, 0, 2, 2, 2, and 4, negative 1. Because this one is not an equation, your domain are just the x values from your ordered pairs. So you would give your domain are the values negative 3, negative 1, 0, 2, and 4. And they would go into those brackets like you see there. For one like example B, however, where you're given g of x is equal to negative 3x squared plus 4x plus 5, this one gives you an equation that x is not in the denominator, nor is it inside a radical. So for this one, your domain would just be all real numbers. So from negative infinity to positive infinity, because you could literally plug in anything for x. So for your next part, the next example, you have h of x is equal to 1 over x plus 5. So for this one, you are just going to take what's in the denominator, since x is in the denominator, set it not equal to 0. So plus 5 cannot equal 0. Because anytime we have 0 in the denominator, it's undefined. So we're going to move that 5 over, subtracting it from both sides, and you have that x cannot equal negative 5. So your domain would just be x, anything other than negative 5. So x cannot equal negative 5. If you were to write this in interval notation like we did in the beginning of your chapter, which I'm not going to require you to do, you would go from negative infinity up to negative 5 with a union from negative 5 to positive infinity. So that just represents that it's every number other than negative 5. If we look at some extra examples from what we did yesterday, we're evaluating each of these functions. So for number 1, it gives us f of x is equal to 4x plus 2. We're finding f of 8. So we're just going to take that 8, plug it in for x, and simplify. So that's going to give us 4 times 8 plus 2. Your 4 times 8 is 32, plus 2 gives you 34. For number 2, we have h of x is equal to 4x minus 2. We're finding h of negative 9. So we're just going to plug in that negative 9 for x. So it's going to give us 4 times negative 9 minus 2. The 4 times negative 9 is negative 36. Minus 2 is negative 38. So h of negative 9 is equal to negative 38. For 3, we have f of x is equal to 4x plus 1. We're finding f of 3. So that means we're going to have 4 times 3 plus 1. Your 4 times 3 is 12, plus 1 gives us 13. So f of 3 is equal to 13. For number 4, we have g of x is equal to 3x minus 5. We're finding g of negative 2. So we're going to plug that negative 2 in for x. That's going to give us 3 times negative 2 minus 5. 3 times negative 2 is negative 6. Minus 5 gives us negative 11. So g of negative 2 is equal to negative 11. For 5, we have f of x is equal to 3x minus 5. We're finding f of 2. So it's going to give us 3 times 2 minus 5. The 3 times 2 is 6. Minus 5 is 1. So f of 2 is equal to 1. For number 6, we have w of a is equal to a minus 1. We're finding w of 0. So that's just going to give us 0 minus 1, which is negative 1. So w of 0 is equal to negative 1. For 7, we have w of n is equal to n minus 1. We're finding w of negative 4. So with this one, we're just going to have negative 4. Let's do this, because this is really little. Negative 4 minus 1, which is negative 5. So w of negative 4 is equal to negative 5. For 8, we have w of n is equal to negative 2n minus 1. We're finding w of 3. So that's going to give us w of 3 is equal to negative 2 times 3 minus 1. So that's negative 6 minus 1, which means w of 3 is negative 7. For number 9, we have h of n is equal to 3n minus 4. We're finding h of negative 6. So that means we're going to have 3 times negative 6 minus 4. Your 3 times negative 6 is negative 18. Minus 4 gives us negative 22. So h of negative 6 is negative 22. For 10, we have f of x is equal to 2x plus 1. We're finding f of 3. So that means we're going to do 2 times 3 plus 1, which is 6 plus 1, which gives us f of 3 is equal to 7.